Yeah, good afternoon, everyone. So today we will discuss about the next chapter of the fluid and particle mechanics, which is the non-Newtonian fluids. So maybe before I start today's lecture, maybe I would like to sorry first to you all because actually in this subject in fluid and particle mechanics, I think you already know that the content, the syllabus is quite dense. So actually, we still have two chapter, which is non-Newtonian fluids that I will give you today, and the last one is about the mixing. So I understand. I think this week is already the last week of the semester, so I understand if some of you or maybe most of you are already tired with all the exam, all the assignments. So please bear with me. So today, actually our schedule is only 1 hour, right? So, but I think maybe I cannot finish these topics only in 1 hour. But if I extend to our next class, it will be very nanggung gitu ya. So I hope I can finish this non-Newtonian fluids in 1 hour. But if not, then please again bear with me for another maybe around 15 or maybe 30 minutes more. So we will finish today's class later than 2 o'clock. Okay, I hope it's okay with you. And some of the content is basically just some of the concept is actually I already teach you in our first class. Is about the non-Newtonian fluids is basically the other type of the fluid which not follow the Newtonian law. So but the Newtonian fluids I have already explained to you in our earlier topics. So please, if you already forget about that, please restudy the topics again so you can connect that information with today's topic. Okay, let's continue our discussion. Okay, so basically, why in fluid and particle mechanics? Actually, we go back to only fluid mechanics, because in non-Newtonian we do not discuss about the particles. Although if you mix fluid, if you transport liquid together with solid particles, the behavior of both fluids, the behavior of the fluids can transform into semi non-Newtonian fluids. But this one we will not discuss in today's discussion. So basically, for these non-Newtonian fluids in fluid and particle mechanics, is basically introduced to you what will be the differences between these non-Newtonian and Newtonian fluids. And later, this factor, well, I think you already, you still remember, right? We use Bernoulli equation, and then we calculate the friction, the loss of energy during fluid transportation. Because the energy is lost, then you need to supply energy inputting device such as pumps or blower or compressor. So basically, in non-Newtonian fluids, the case is the same. Just the behavior of certain properties is different. Yeah. So in these topics, I hope after studying about this topic, you can differentiate between what will be the Newtonian fluid and what will be the non-Newtonian fluids, and what will be the difference in fluid flow calculation. Yeah, especially in the correction for the power required to flow non-Newtonian fluids. Because when you flow non-Newtonian fluids, it's same with the Newtonian. You will have pressure drop. You will have energy loss. Then you will need to supply additional energy. Yeah. So the outcome, students should be able to recognize what will be the differences between the Newtonian and non-Newtonian fluid, especially the simple one, the incompressible fluid. So the proper correction for power loss calculation in non-Newtonian fluids can be applied. So that is the desired outcome. Okay, do you know this one? What is the name of this cake? Actually, I just got these figures just now to represent, okay, this one. Do you still remember the concept of viscosity? What is the viscosity? So if you have, this is the, you have two parallel plate, yeah, two parallel plate, yeah. This one is the static one. The bottom one is the static one, and the top one is the moving one. So if you apply force to the top plate and you have a fluid in between, so you can imagine you have fluid, and you may imagine that the fluid has layers. Yeah, has layers like this. So maybe you can imagine like this. Okay, I think you already have lunch, right? So it's okay to see food like this. Okay, so if you imagine the fluid have layers like this, and then you move along the top plate, yeah, this is the moving plate with certain amount of forces. What will happen with these layers of fluid? Yeah, of course, the first layer will move with the same velocity. Yeah, the first layer will have the same velocity with the top plate, because you can imagine this very first layer, the very top layer, is connected to the top plate. Yeah, so the velocity, you can assume, you can say that the velocity of the first layer is the same of the velocity of the top plate, the moving plate. How about the layer after the top layer? Will they move with the same velocity? Apakah kecepatannya sama untuk layer-layer di bawahnya? Is the velocity of the second layer, maybe the third layer, the fourth layer, and so on? Will they have the same velocity as the first layer? Anyone can guess?
Will it be different, sir?
Yeah, it will be different. Higher or lower with the first layer, the velocity of the second layer.
Is it higher, sir?
Why it's higher?
Because there's no friction, sir.
Okay, are you sure?
I don't know. I'm just guessing, sir.
Okay, so you can imagine, right? The layer is like this, and then the top one, the top layer, you move it, yeah, with a certain velocity, with a certain force. So the first layer will move together with the top plate with the same velocity. But there will be friction, right, between the first layer and second layer. The second layer will move to the right direction. However, the velocity is decreased because between the first layer and the second layer, you will have friction. Yeah, you can imagine each of layers give friction to one another. That's why the second layer will also move to the right direction, but the velocity is decreased for the second layer. Yeah, the velocity will be decreased, right? How about the third layer? It will move, but the velocity is also decreasing. So the velocity of the third layer, fourth layer, until the bottom layer, it will keep decreasing. It will be keep decreasing, right? And you can assume at the bottom layer, the very bottom layer, that adjacent to the static plate, it will have no velocity, right? Yeah, you can imagine the movement of each layer is like that. This is the case when you have bottom plate is in static condition, it's not moving, you just move the top plate. So there will be the gradient of velocity. Yeah, you will see the gradient of velocity. This one, this one, this one, this one. Yeah, we call it du or dv. This one is actually the same, right? Velocity over dr. It's called the velocity gradient. Yeah, it represents the change of the velocity along r position. Or in our first, maybe if you check with the previous slide is du over dy. This is y direction. Don't be confused with the letter, yeah. So you will have velocity gradient along radial direction. Yeah, because when you see from top to the bottom, the velocity is different. Okay. How about so first you apply certain force. If you increase the force, what will be the velocity? Kalau Anda menaikkan gayanya ya, gaya dorong ke kanannya dinaikkan, if you increase the pushing force to the right direction, what will be the velocity? Will it be increase or decrease?
Increase, sir.
Sorry, Galang?
Increase.
Yeah. If you increase the force, then the velocity is also increased. How about the second layer? It will still lower than the first layer. However, along way, the du over dr is also increased if you increase the force. You can get this concept, right? So basically, the velocity and the velocity gradient will be influenced by how much you apply the force to this system. Okay, now we go back to what is Newtonian. You remember this is the shear stress. Shear stress is basically shear force divided by area, right? Yeah, tau will be F divided by A. But you can also correlate tau, the shear stress, with gradient of velocity. Yeah, if you increase the shear force, the pushing force is the shear force, right? In the certain area, yeah, for the certain area, the area in this context is the area of the plate, yeah, luas area papannya, yeah. If the area is constant, but if you increase the shear force, the pushing force, then the shear stress will also increase, right? The shear stress increase, du over dr is also increase when you increase the shear force. So if you increase the shear force or you increase the shear stress, the change or the increase of velocity gradient is linear, it means it's called Newtonian. Ya, jadi kalau Anda menaikkan shear force atau Anda menaikkan shear stress, kemudian gradient velocity-nya itu naiknya juga linear ya, it means when you increase the force 2 times, or if you increase the shear stress 2 times, then the velocity gradients also increase 2 times, it means it's linear. Or if you increase 3 times, 4 times, 5 times, and so on, if it's linear, then you will have the value of the absolute viscosity, or yeah, this is the absolute viscosity, and it's constant. This is for Newtonian. So if you plot the shear stress with the shear rate is the velocity gradient, and you will have a exactly straight line, the fluid will be the Newtonian. Yeah, this is the concept of Newtonian fluid. Yeah. Do all fluid follow this behavior? Of course not. Some, yeah, some fluid will have behavior like this one, Bingham. Bingham, if you see, this is the straight line, yeah, but it's not start from zero. It means you will need to apply higher shear rate, yeah, you need to apply the higher shear stress until the fluid can flow. If you have shear rate, if the shear rate value is higher than zero, it means the fluid is starting to flow. Yeah. So you need to apply higher shear stress, then the fluid start to flow, then the profile is linear. So it's the same as Newtonian. However, it doesn't start from zero. That's the example of non-Newtonian fluid, which we call Bingham plastic. Or the other, like dilatant pseudoplastic, the movement of the fluid start from zero. However, it's not linear. It's like this one, yeah, or this one. We call it also the non-Newtonian fluid. Or it's like Bingham, but not linear, but have slightly curved. It means the change of shear stress. If you see the line is not a straight line, it means shear stress is not linear with shear rate. Yeah. So in pseudoplastic, Bingham pseudoplastic, and dilatant, the change of shear stress is not linear with shear rate. Ya, tidak linear. Kalau garisnya tidak lurus, itu artinya tidak linear, gitu aja ya. So the profile of example of the profile of non-Newtonian fluid can be like Bingham pseudoplastic, the pseudoplastic, or dilatant. The Bingham, the differences is it's not start from zero shear stress. You need to apply higher shear stress. It means you need to apply higher force so the fluid can move. So that in order that the fluid can move. Okay, any question until this part? So in summary, basically certain fluids will give a certain amount of resistance. Yeah, the shear rate is basically the resistance because it has layers on it. The fluid has layers. The magnitude of the resistance, yeah, will decide or will influence how fast the movement of the fluid. It means if the fluid doesn't give much resistance, it will easy to move. Yeah. So if the viscosity is low, it means less resistant. If less resistance, easy to move. However, if mu is higher, then high resistance. High resistance means difficult to move. That's why sometimes viscosity in general term, you can explain it like how thick is the fluid. If the liquid is very, very thick, then the viscosity is high. If the fluid is very, very thin, then the viscosity is low. So it represents the resistance. In real case, some fluid, the resistance magnitude is not always linear with the force. Yeah. So if you have a constant resistance, we have discussed, it's like the Newtonian one. If you increase the force, you increase the stress, then the shear rate is increased. It means, and it increased proportionally. It means it's linear. But some in non-Newtonian, it will not the same. It will not linearly increase. Okay, any question? I hope you can start imagine, not the cake, but what will be the liquid or what will be the fluid looks like. Yeah, sorry. Okay, so this one I have already explained. in mu is the absolute or dynamic, right? Dynamic viscosity. Viscosity. For Newtonian, mu is constant. For non-Newtonian, mu is not constant. Just this is the difference. And in non-Newtonian, yeah, we call it apparent viscosity. Yeah, because the way it's called apparent, because if you have Newtonian is like this, right? At this value of shear rate and shear stress, yeah. In Newtonian, basically mu is the gradient, right? Gradient or the slope of this line, because tau is minus mu du per dr or dv per dr. Why minus? Because the direction is because it shows the resistance. So the direction is in the opposite direction. So in Newtonian, this is Newtonian. Basically, mu is the slope. So when you take at this point, the line, yeah, the slope is constant, right? Slope is constant. So the mu is constant in Newtonian. However, in non-Newtonian, for example, in pseudoplastic, if you see the gradient in this part, this part, this part, and this part, it might not be the same. It's not constant. Why? That's why we call it apparent viscosity. So it's like this viscosity at certain point. That's why we call it apparent viscosity. Yeah, because the magnitude of the resistance is not always the same for every shear rate that has been given. In addition, for Bingham is always not start from zero. Yeah, for Bingham fluids, you need minimum shear stress. Yeah, we call it minimum shear stress in order the fluid can move, so that the liquid can move. It means it requires minimum shear stress that's to be given to overcome the resistance. Ya, jadi untuk yang Bingham itu ada tambahan ini, shear stress awal untuk mengovercome tahanan yang diberikan oleh fluida. Oke. Okay. The previous figure, the previous slide, the figure is between shear stress and shear rate. Yeah. This figure is between the measured viscosity or apparent viscosity. We use this one. Don't be confused with the symbol, right? This is the measured or apparent viscosity. Do you know the device that use the name of the device that that is used to measure viscosity?
Viscometer.
Viscometer. But for non-Newtonian, it's normally called by rheometer. So it's to analyze the rheology of the fluid. Rheology is the behavior of the fluid. So if you compare, yeah, between the measured viscosity or apparent viscosity with time, yeah, this is shear stress exposure period. It means the value of shear stress is the same. Yeah, you apply certain shear stress or you apply certain shear force. However, the duration is different. Like you give like what is the unit of shear stress? If it's force divided by area, what will be the unit? Newton over square meters or Pascal. or basically this is pressure, right? Same like pressure. So for example, if you give 10 Pascal of shear stress, but you vary between maybe 10 seconds, 30 seconds, 1 hour, 24 hours, 1 day, 24 hours and 1 day, same, right? 1 day, 3 days, 7 days, or something like that. Yeah, but you give constant value of shear stress, for example, 10 Pascal. Then you vary the exposure time or exposure period. For Newtonian, the curve or the graph will be straight line. It means if the shear stress value is constant, no matter how long the time of the duration, yeah, the value of viscosity remains constant. So it doesn't change with time. That's for Newtonian. However, for non-Newtonian, sometimes it's increase, sometimes it's decrease. Yeah. For the top one, yeah, the fluid that the viscosity is increased with time, although the shear stress value is constant, we call it rheopectic. Yeah, the apparent viscosity is increased during the shear stress exposure period. And the opposite, we call it thixotropic. The apparent viscosity is decreased. I don't give the example, but maybe later you can open the YouTube. You can just search this rheopectic and thixotropic. You can see there's some experiment that has been done to compare what will be the liquid. Normally, non-Newtonian is liquid one. You can see what will be the differences in the liquid's behavior with time. Okay, so this is the example. The Newtonian, we can call it, the example is water. Yeah, water is the perfect example of Newtonian, but actually some oils, honey, or fruit juice is Newtonian. So it doesn't necessarily that all viscous fluid, ya, tidak semua fluida yang viskositasnya tinggi atau kental itu non-Newtonian. However, some fluid like apple puree or maybe cornstarch suspension or tomato ketchup, yeah, toothpaste is classified as non-Newtonian. Fruit jam is non-Newtonian. So you can see from water is just water, and then you put some fruit concentrate, become fruit juice, that is still Newtonian. But if there's some solid, it will be dilatant or pseudoplastic. If you increase the content of the solid, then it will be Bingham. So sometimes it's true that if you increase the solid content, it will change the fluid to be less Newtonian. Okay, any question until this point? I think I have to change the... Okay, maybe to enhance your understanding about the concept of Newtonian and non-Newtonian, you can watch this very short video.
Hello, and welcome to another Science Man digital lesson. Today, we're going to take on the interesting topic of Newtonian and non-Newtonian fluids. A classic Newtonian fluid is water. Water has a very predictable viscosity and will always flow predictably regardless of the forces acting on it. Newtonian fluids also have predictable viscosity changes in response to temperature and pressure changes. To investigate the properties of Newtonian fluids experimentally, let's start with some warm honey. As you can see,
Ya, suara videonya kedengaran kan ya? You can hear the sound of the video?
Yes, sir.
Okay, so in this video, basically, it will compare certain types of fluid, yeah, and then you can see they for each liquid they do two types of experiment. First, they put the ruler and see if you dip the ruler and then take out the ruler, what will be the behavior of the liquid, and then the second one they punch the liquid with the hammer. You can compare what will be the differences.
see here, warm honey flows easily, and it will easily flow around objects, such as this ruler. Placing a force on the honey has no effect on its viscosity. Even if we place a large force on it with a hammer, the honey predictably flows around the hammer. If we try the same thing with cold honey, we see, as you would expect, the honey is more viscous. That is, it flows slower. But when we test it with the ruler, we see it behaves much like the warm honey. It's the same when using the hammer. Applying a force has no effect on the viscosity. Honey, whether it's warm or cold, is a good example of a Newtonian fluid.
Ya, jadi kalau madu dicoba dalam kondisi dipanaskan atau dalam kondisi dingin ternyata sama. Jadi sebetulnya sorry if I use Indonesian language. So actually when you dip the ruler or you use the hammer, it's basically it's the visualization of applying a certain value of forces or certain value of shear stress. And you can see that the behavior of the honey is the same. So it doesn't change the behavior of the viscosity. So honey is the example of a Newtonian fluid.
Let's try a different fluid. We'll perform the same test with cornstarch solution. When you pour this solution, it appears to behave much the same way as the honey. When you place a ruler into it slowly, the fluid flows around the ruler. However, when you attempt to force the ruler into the fluid instantly becomes more viscous. Hammering the fluid with even more force produces even more resistance to flow. Because a cornstarch solution's viscosity changes with an applied force, it is a non-Newtonian fluid. Unlike a Newtonian fluid, applying forces to this non-Newtonian fluid causes its particles to behave more like a solid. This makes the behavior of non-Newtonian fluids very strange. As you can see here, even though cornstarch solution flows when emptied from a bucket, you can't break its surface even when using a sledgehammer. You can even jump on and off a cornstarch solution. Just remember, don't stand on it, as you will eventually sink.
Yeah, tadi you can see from the cornstarch experiment, right? It shows different behavior when you are using ruler compared to when you are using hammer. Or if you put it to the bigger container, and then you can jump on the top of the cornstarch, and you will not sink if you just do it like that. But if you stand still, it means the duration of the contact or the duration of the force is longer, then your feet will sink into the cornstarch. That's the example of the non-Newtonian.
So in summary, non-Newtonian fluids have unpredictable responses to applied forces. With applied forces, they become more viscous, such as cornstarch, or less viscous, like ketchup. What other fluids might you suspect to be non-Newtonian fluids? Try your own fluid.
Okay, yeah. So some non-Newtonian, if you apply higher force, like the cornstarch, yeah, you jump like that, it means you apply higher force, it will give higher resistance. But if you just stand still, it will give less resistance. That's why the feet is sinking. But some other non-Newtonian, when you apply more force, like tomato ketchup, it will flows easy. But if you just give small force, it will difficult to flow. It's also non-Newtonian. I think from that visualization, you can differentiate what will be the difference. Maybe it's you already know in your daily life, but maybe you don't really pay attention to that behavior. Okay, maybe later we will not discuss this one, but for your thought at your convenient time, you can check whether for any incompressible fluid, is it true that if the viscous apparent, the appearance of the liquid, if it is more viscous, is it indicating that the fluid is non-Newtonian? Well, of course, from the honey example, it will not. But you can try to find another types example of what will be actually classified as Newtonian or non-Newtonian fluid based on its apparent viscosity, whether it's thick or thin liquid. Is it always true that thin liquid is always Newtonian? Yeah, you can check by yourself. Okay. Any question? Sorry. Okay. Now we go into the equation. Just don't get intimidated with the equation because later the equation become more complex. Just want to show you the comparison between the figure and the equation. Yeah. From the figure, basically this is the comparison between shear stress and shear rate. Yeah. The left hand side is shear stress, the right hand side is shear rate. Okay, for Newtonian, it's linear. Yeah. For non-Newtonian, but non the Bingham, it can be like this one or it can be like this. Basically, it follows certain order of power law. It means it will not linear. Yeah. This one is actually like this. N, but N equals 1. Yeah, this is for Newtonian. For this one, N can be between 0 and 1, and N can be over 1. That's why the curve can be like this, or the curve can be like this. Yeah, this is the order, yeah, and this is the apparent viscosity. Again, don't get confused with the symbol. Sometimes it's K, sometimes it's like this. But this represents the apparent viscosity. Okay, special case for the Bingham, for the Bingham is basically the general case will be tau 0, tau 0 is this one, this is the tau 0 plus this one. Actually, you have N also, and the constant, you have the order and the apparent viscosity also. But if the Bingham shows linear straight line, it means N equals 1. But for the pseudoplastic Bingham like this one, so the N will not be equal 1. But for the Bingham, you will always have the initial value of shear stress. The graph doesn't start from 0. For power law or for Newtonian, tau 0 will be equals 0, right? Because there is this one. Because in the graph, it starts from 0. Yeah, this is the first equation. Yeah, so for the Bingham, normal Bingham, it's like this. But for the Bingham pseudoplastic, so you just like this. Over N. Okay, any question until this point? Yeah, this one equals tau yield is equals tau 0. Yeah, this one. Okay. Okay, and then I hope you still remember about this equation. It's called Haagen-Paas equation. This equation, we discuss it when we discuss about the fluid flow, correlate between the flow rate and the pressure along the pipe. Yeah, so Q is the flow rate. This one is the symbol change again. This one is viscosity. Yeah, this one is viscosity. This is the flow rate. P1 minus P2 is the pressure difference. R is the radius of the pipe. Yeah, L is the length of the pipe. Okay, radius. If you use a certain type of pipe, yeah, it will have certain length and certain diameters. So both R and L is constant. Yeah, you can imagine that, right? So for certain shape of pipe, so the value of radius and the value of the diameter is constant. So basically, from this equation, this one can be put into one constant. Yeah. So you P if of course a constant, right? So P R4 divided by 8L, you can group as one constant. So you move along all the constant to the left side. Together with the viscosity, you can have this correlation. Yeah. So all the constant parameters, you group it together. You just consider it as one parameters. And then you compare between Q, viscosity, and pressure difference. You have linear correlation, right? Yeah. If you see from this equation, you will have linear correlation between Q and delta P, as long as this one is constant. Yeah, as long as the viscosity is constant. You have linear correlation between the flow rate and pressure difference. If viscosity is constant, then it is the Newtonian fluid. So basically, this why I bring up this formula, so you can get the concept that in Newtonian fluid, if you increase the velocity, if you increase the flow rate, then you will increase the pressure drop. Yeah, in a certain arrangement of pipe, certain diameters, certain length, yeah, and you flow the Newtonian fluid. If you increase the Q, you increase the flow rate, then you will have higher pressure drop, and the increment is linear. That's for Newtonian. That's we have learned so far in our previous discussion. Okay, how about non-Newtonian? Basically, you can modify. Yeah, you can modify the equation. If for Newtonian, the formula is this one. Yeah, yeah, the formula is this one. For non-Newtonian, you just put the order in this Q parameters. Yeah, for any non-Newtonian, then the resistance is not the same, right? The resistance that given by the fluid will not be constant, right? Yeah, if you increase, maybe the resistance is increased, or maybe the resistance is decreased if you increase the shear stress. So there will be some value of the correction of the resistance. You put it as the N value. Okay, for Bingham, N is equals 1, yeah. For Bingham, normal Bingham, N is equals 1, but you will have initial pressure to overcome the shear stress. For Bingham, but not the normal one, then you will have this one. Okay, for this one, N is equals 1. Okay. Okay. Now, please remember again about the Bernoulli. In terms of specific energy, what will be the value? P1 over GZ1. This one, right? Minus EF. Just be careful. Now we introduce this one. This one, right? I hope you still remember. Okay. What is EF? EF is the energy loss with the unit of specific energy that caused by friction. Friction between the fluid and the pipe wall, the inner pipe wall. So it will decrease, it will reduce the energy input. How to calculate EF? EF is basically this one. Yeah. Remember again how to calculate EF. EF is 4 times friction factor times L over D times this one. So to calculate EF, you need to calculate the friction factor. And friction factor will be the function of Reynolds number. And Reynolds number will be the function of viscosity. For Newtonian fluid, viscosity is always constant. So it won't be any problem. You just need to calculate the Reynolds number. Reynolds number can be calculated using this one. And then you can calculate F, yeah, using equation or using the graph. And then you can calculate EF. Then from EF, you can put it into the Bernoulli. How about the non-Newtonian? For non-Newtonian, the viscosity is not constant. So there will be some correction in calculating the Reynolds number. And then some correction to calculate friction factor. But the formula to calculate EF is the same. Yeah, we just need to just a bit modify how to calculate the friction factor. And how to calculate the Reynolds number is basically, okay, maybe we can go to this one first. Yeah, there is some equation. Yeah, you do not need to memorize. Yeah, there is some equation that can be used to calculate Reynolds number. Yeah, this is the formulation. Yeah, a bit complex since you need to calculate. This is the average velocity. Yeah, and then N is the order. Yeah, from the previous equation. Yeah, this one. N is this one. Yeah, unit K. Yeah, K is this one, the apparent viscosity. Yeah, you need to put it into this formula. Or you can use certain types of graph. Although the graph is very not very, it's limited and it's only applied for certain case. That's why you can, but still you can use the graph. But from this equation, you need the value of average velocity, right? So the average velocity you can calculate from this one. This one is point velocity, yeah? Point velocity. For point velocity, it means like if you have pipe, yeah, this is RW. RW at this one is the radius of the pipe radius. So if you want to know the certain point, maybe at this point, this one, yeah, R will be less than RW. So you can use the this equation. U or velocity equals blah blah blah. So this is the formula if you want to measure the velocity at certain point. At R equals RW, the velocity will be 0, of course, yeah. Exactly at the pipe wall. This is the different case with with what I have explained in the first slide. In this one, this is the pipe, yeah, and the liquid is flowing like this. So exactly at the pipe wall, the velocity will be 0. R equals LW, the velocity will be 0, yeah, from this equation. Then how to calculate the average velocity? To calculate average velocity is basically you need to calculate the flow rate divided by area. Okay, if the value of the flow rate is known and the value of the pipe diameter is known, then you can directly calculate the average velocity. Ya, jadi kecepatan rata-rata itu sebetulnya tinggal laju alir dibagi luas penampang, cross sectional area. Ya, this is flow rate. Just divide it, then you can get the average velocity, then you can put into this one. If you know the value of the flow rate. But sometimes the calculated one is not, or the measured one is not the flow rate, but the axial pressure difference. Yeah, dP over dx, or maybe minus dP over dl, same, right? This is the axial direction. Axials mean the direction along the pipeline. Okay, if you have the value of the dP over dx or dP over dl, then you can calculate the Q using this equation. So it will depends on what kind of information that you have. If you have the value of dP over dx, then you can use this equation. Then after you have Q, then you have D, right? D is diameter. You can calculate the area, just divided Q divided by A. Can be understood, right? That's how you can get the average velocity. The problem is you need N value. You need K value from this one. Yeah. If you have, maybe we can go back to the gambar. The gambar is, yeah, can use this one. Okay. Yeah. This is Newtonian. This is non-Newtonian. For the Newtonian, tau will be mu dV per dr. For non-Newtonian, yeah, non-Newtonian, tau will be, I'm using, I think I can use the other, just a sec. Minus K dV over dr N. Yeah. If you have the value of tau and you have the value of this one, how to get the value of N and K? If you already have this graph, yeah, so you have this one. You have the value of this one, for example, yeah. First point, and then the second point. Then the third point, how to get the value of K and order?
You can rearrange it into y equals to mx plus c.
Y to, for this one, the intercept is 0. So your problem is to get what is the value of K and what is the value of N based on this equation. If you just plot this one, it's difficult. Yeah. If you directly plot the shear stress with the shear rate, yeah, you can use MATLAB or you can use other optimization graph, yeah, to get the K and N. But if you do not have those kind of simulation tools, you can make this equation linear, right? If you have this equation, how to get this equation become linear?
Take the natural logarithm.
Yes, correct. You can take the natural logarithmic or you can take the logarithmic one. So you can plot between log tau and log shear rate. You will have N as the slope, ya. So the equation, tadi persamaannya di mana ya? Sorry. Yeah, from this equation, yeah, you can have this one. This one, right? So if you plot log tau with log dv over dr or du over dr, then you will have straight line, yeah, with the slope of n. So this is the slope and the intercept of this one. Then you can have the value of x and, sorry, you can have the value of K and N. Any question until this part? Then if you can have this value of K and N, you can use this equation. Okay, any question? I hope it's not too complicated. Yeah, and then you can calculate the average velocity, and then you can calculate Reynolds number, and then you can use certain graph which can be applied to your system, of course, to calculate F. After you can have, if you can calculate F, then you can use this one. The question remains the same, yeah, just correction in F. Actually, there are some, we call it what, empirical formula for a certain types of non-Newtonian. For example, this is the Bingham, the condition is turbulent. Then you don't memorize this equation. No need for you to memorize, just burden your brain if you memorize this one. You can use this, we call it Hedstrom number. Then from the Hedstrom number, you can put to this equation to get the value of friction factor. Okay. This one I will skip because I don't know how to explain it in the simple way to you, and I think you do not need to understand this in this semester. Just pay attention to this one, yeah. This one, yeah, this one is du over dr. This one is tau, and this one is the apparent viscosity. Yeah. So by using the formula that tau is minus mu du over, oh, I think I'm using the wrong by using this one. Yeah, this one is this one. Yeah. Please later do it at your convenient time. What will be the value of n? Yeah, by using this combination of data. And then you have D is 37 millimeters. This is dP over dL, yeah. So it's same, dV over dL is equals dP over dx in the previous formula is 1.1 kilopascal per meter. Then calculate what is the average velocity. Yeah, first you need to get the n value first. You need to get the k value, yeah. Okay, then you need to get the k value. So okay, maybe the equation is not complete. Tau is minus k mu a, this one. So for this problem, solve using this equation. The data is already provided, yeah. This is the tau, this is the shear rate, and this is the apparent viscosity. Then calculate the k. You just take the log plot, yeah, log between tau and log Vs log mu a times this one. Then find, no need to pay attention to this table, just whether you can get that the average velocity is this one. How to calculate? From this figure, yeah, log tau, Vs log blah, 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 then you can get K and N, right? Yeah, so you can get K and N, you have the value of dP over dL, then you can get the Q. From the diameters, you can get the A cross-sectional area, then you average will be Q divided by A. Okay, any questions so far? I hope I'm not explaining too fast to you, and I hope you can get the basic concept of non-Newtonian. This answer is basically calculated using this equation, but this equation is very, very complicated. So just skip this one. Just use the path that I suggest you. Yeah, you plot between log tau versus log. You can take natural logarithmic. It's the same, mu a times shear rate. Then you can get the linear. This will produce a linear straight line. Then you can get the slope. The slope is n. The slope is n, and the intercept is log minus k. Then you can get this one. Then after get k and n, you have this one, right? dP over dl. Yeah. You can put it into this equation. All the information is already complete, right? You have n, you have k, dv over dx is dp over dl, the same. The pipe radius, half of the diameters. This is the diameter. You can use either this equation or this equation. Then you can get q. From the diameters, you can get cross-sectional area. I think you still remember, right? Cross-sectional area is this one. Okay. Okay, any question? So basically, to close this subject, for third semester of chemical engineering student, the non-Newtonian topics is just the introduction. I think you can differentiate what will be the behavior differences between non-Newtonian and Newtonian. Whether it's in the physical appearance and also in mathematical formulation. And if you flow the non-Newtonian, then there's some correction about how to calculate Reynolds number, and then how to calculate friction, and how to calculate the energy loss. But after you can get the value of energy loss, basically how to put it into the Bernoulli equation it will be the same with Newtonian. Just a bit complex in the calculation of parameters that requires viscosity value, because in non-Newtonian, the viscosity is not always constant along the time, along the way, along the force. Yeah, and the data of the apparent viscosity, I have told you, it's called it's obtained from what we call rheometers. So the data is basically you can, from the rheometers you can get the plot, yeah, between the tau and du over dr. Then after that you can get the k value, you can get n value, then you can use directly this value to calculate like the flow rate, and then to calculate the Reynolds number, and then to calculate the friction, and etc. Okay, any question? Am I explaining too fast?
No, sir.
Hopefully no. Okay, that's all. This all the materials for non-Newtonian fluids. As I promise you, I will keep it to 1 hour, but if it's more, then it's not more than 30 minutes. Okay, I suggest you to redo this calculation, yeah, using the steps that I have explained to you. Then try whether you can get this value. Or if you have any question relating the concept or relating the equation, or maybe relating how the calculation should be done, yeah, then you can text me to WhatsApp. It's okay. Of course, I will answer in my convenient time, but it's okay. Okay, I think that's all for today. So in our next class on Thursday, 2 hours, hopefully I can finish the mixing subject. Mixing is actually not so what? It's not that difficult to understand, yeah, and the equation is not that complex. Okay, thank you so much. Good afternoon, and we always take care of your health, yeah. Just take precaution of the protokol kesehatan, and we'll see you again on Thursday in our final last class of fluid mechanics. Okay, thank you. Good afternoon. Bye-bye.
Thank you, sir.
Thank you, sir. Thank you, sir.
Yes, sir.
Thank you, sir. Stay happy.